Hello everyone. Today I will share our work for FwdLLM, that is efficient federated fine-tuning of the large language models with perturbed inferences. And this work was done in collaboration with Professor Mengwei Xu and Professor Shangguang Wang and two master students Yaozong and Xiang. So let's get started. And first of all, I will quickly introduce the background of this work, that is a federated large language model, and we just call it as a FwdLLM for short. And different from the previous two papers that focus on the training within a data center, and FwdLLM focuses on the federated learning of large language models across different data centers. And all of the central training, distributed training, and federated learning, all of those training methodologies, they can all generate strong large language models to support various downstream tasks, right? Like the classification, question answering, and generation, and so on. And the uniqueness of the federated learning is that it does not collect the data together, and instead it transfers the model from one data center to another data center. And so it can use the computation all over the world, and most importantly, it can preserve the data privacy so that it can leverage more private and personalized data more eagerly. And as a result, FwdLLM can democratize LLMs and can make more stronger LLMs in the future. However, such a good vision has some fatal drawbacks. So the first drawback is it needs to run LLMs training within those edge devices or mobile devices, and those devices is usually memory limited. So training LLMs in those devices will lead to an unaffordable memory footprint, and that's the first challenge. And the second is about the hardware incompatibility. And as we all know, there are continuously new accelerators on the mobile devices, such as NPU, TPU, and it can process the data up to 30 times faster than the CPU. And its speed up advantage is increasing linearly over the years. And ideally, with NPU, TPU, we can compute every model very resource efficiently on the mobile devices. However, unfortunately, for the current NPUs, it doesn't support many of the operators for training. And we have more details in the paper, and so we cannot compute those models with NPU right now. And the third issue is a special issue for the federated learning. And during our experiments, we find that even we have thousands of the clients simultaneously, not all of those clients can contribute to the training at the same time. And for example, if you use 20 clients for each round training, it is already enough to saturate the learning knowledge of each gradient updated. And this issue can be traced back to the scalability issue of the batching. And we also have more explanation of this issue in the paper. You can refer to more details. And we attribute all of these three issues to the backpropagation-based gradient computing. Because during the inference, we all know that we do not have the gradient computing, right? So we do not have that huge memory usage because we do not need to store those intermediate activations to update those gradients. And we have a better hardware compatibility because we have a lot of advanced optimizations from the companies, from the academia. And so we are thinking about, is there a way that we can just alternative those BP-based training? And or just say, is there any way we can do the BP-free training? So fortunately, there have been a lot of previous mathematical literatures that point this way out. And as shown in the timeline, I listed the main milestones of the BP-free training. And from 1988, Karls first proposed a method that estimates the mean of multivariate normal distribution. And after that, a series of the zero-order optimizations are proposed and continuously being studied. But BP-based method, as you know, has become the mainstream and quickly developed due to its precise gradient computation. However, recently, in 2022, Professor Hinton, who starts the deep learning research wave, proposed a forward algorithm to recatch researchers' eyes to those BP-free training. So some new methods that can better fit the deep learning models are proposed after that. So in this work, we choose one from them, and that is the forward gradient, and we take it as our algorithm foundation. So let me quickly introduce this method. As you can see, here is a BP-based forward gradient, BP-based gradient, or we can just call it as a true gradient. And I skipped the details about how to compute those BP-based gradients because we have a lot of materials to ref. And I just want to show how forward gradients can estimate those true gradients. So first, we will generate some perturbations V in different directions. And these are the yellow arrows, if you can see it. And then we will add those perturbations to the model weights and see how it acts. And the concrete way is to see the variations of the loss function f. And that means we compute the f theta plus hv, and that is the loss with a perturbed model. And we minus it with f theta, and that is the original weights. And we divide the results by a very small number h, and it's just like a way to compute the directional differential. And after that, we just multiply the computed directional differential with perturbation V to gain the forward gradients. Okay, here's a little bit complex, right? So allow me to summarize in a word. We just do 3 steps to get the forward gradients. And the first step is inference. We just execute the inference with the original model weights. That means without any perturbations. And the second step is we generate some perturbations. And the third step is that we apply those perturbations to the model, and then we execute those models with the perturbated weights. And we just see what's the difference between those laws. And after that, we can obtain the estimate gradient. So atop on those forward gradients, we implement our system FwdLLM. And as I said in the motivation part, different from the traditional federated learning system, forward-only federated learning system is memory efficient because it only do the inference, and it's hardware-friendly because it only do the inference as well. And plus that, it is very scalable from the perspective of involving more clients. Because if you have more clients, you can have more perturbations, and you can have a more accurate estimation of those true gradients. So now here is a system part challenge. Though BP-free methods are very promising, but none of them has been applied to those large language models. And the reason is that the number of perturbations needed to estimate those true gradients, that is very huge gradients, needs a lot of perturbations. And the real reason behind that is the larger the model, the more is the model weights. And it means a harder task to estimate those weights. And basically, it means the Hessian rank of loss is increasing. And the only way before is to add more perturbations to gain a stable estimation of those gradients. But too many perturbations mean too many inference computation, right? It will narrow our system benefits. So in this work, instead, we first time integrate the parameter efficient fine-tuning with the forward-only fine-tuning. And the parameter efficient fine-tuning only updates a small portion of the pre-trained models and leaves the other parameters untuned. And that will decrease the number of weights that needed to be tuned, right? And during the implementation, we just load the pre-trained model once in the memory persistently and update the small fraction of the separated PFT adapters as parameter efficient adapters, and to help update the knowledge within the model. And the way to update it is just to add in perturbations with inference and do this inference one more time. And the second design is about the client workload adaptation. And the challenge to be further tackled in this design is now we have some smaller perturbations to compute, right? But we still do not know the concrete number to compute those perturbations. And the number of the perturbations has a huge effect on the convergence performance. For example, as you can see in the figure, with a smaller perturbation 1 to 5, that means you only estimate every gradient 1 to 5 times. And you can have sharp accuracy improvements in the early training stage because you can update those gradients very fast, but it will stop at a rather lower convergence accuracy because your estimation is not very accurate. And in contrast, if you insist using the larger perturbations, and then you can undoubtedly have a higher convergence accuracy that will be nearly similar to the BP-based methods, but your convergence speed is lower. So finding proper perturbation numbers is too ad hoc and may even have no best answers because it might be dynamic. So to solve this issue, we just conduct a lot of offline experiments and have a very interesting finding that with the process of the training, you can find that the variance between those computed gradients are becoming more stable. And that finding is useful because during the perturbated inference-based gradient updating, we have a criterion to refer. So once the forward gradient is generated, and we can compute their variance, and this is a very quick process compared to the very complex model inference. And then if we find the variance is turning to be stable, that means the newly perturbation generated does very little help to the gradient estimation. So we just stop generating more perturbations and we do the gradient updating. So if not, we just include more perturbation until the variance is stable. And the third design is about the discriminative perturbation sampler. And typically, we will need thousands or even more perturbations to have a usable or stable gradient estimation. And we dive into those generated perturbations and find that over 60% of the generated forward gradients only contribute to less than 30% of the final forward gradients. So that is a frustrating finding that because we compute a lot of perturbations in vain, and that means we do not compute to the point. So we just propose to filter out those more valuable perturbations beforehand, and by only generating those perturbations that are similar to those contributes to more to when we compute the last round forward gradients. And this simple method can save more than 50% perturbated inference, and for more details, please just refer to our paper. So here is our combined system working flow. And first, cloud will send some seeds and send those seeds to the client together with the pre-trained model. And then the client will sort out those more useful seeds to generate the useful perturbations by using the information of the last run. And then the client will conduct the inference using the pre-trained models and maybe NPUs. And client with the cloud, they will cooperate to validate the global perturbations and make sure that it's enough to estimate this round's gradient. And once the validation is detected, the final forward gradient will be sent to the cloud for the aggregation. So here is the evaluation part, and we implement this system on the mobile devices and on the development board, and we evaluate it on 5 models from the sub-billion models, Albert, Distilbert, BERT, and Robert. Those models are all below the 1 billion models, and we just call them as small models in this work because we still have a billion-sized model LLaMA, is LLaMA 7B. And to demonstrate the system efficiency and the scalability across different datasets, we also conduct experiments on both discriminative tasks and generative tasks. We have 4 datasets in total. And we include 3 types of baselines. The first baseline type is vanilla backpropagation-based federated LLM fine-tuning, and we call it as FwdFT for short. And we have parameter-efficient FedLLM fine-tuning, and we have 3 parameter-efficient fine-tuning methods. That's adapter, bitfit, LoRa. I think it covers all of the mostly used parameter-efficient fine-tuning methods. And the third type is optimized parameter-efficient FedLLM fine-tuning system, and that is FedAdapter. It automatically decides the PEFT configurations. So here is the evaluation results. And first, as you can see in the figure, we can see that the FwdLLM can achieve more than 100 times convergence speedup because it can be compatible with the NPUs, but the traditional BP-based methods, it can only use the GPUs or even CPUs. And second, we show that even with the only CPU and GPUs for our systems, our systems can still outperform those baselines non-trivially. For example, when both using the CPUs for our baseline and for our systems, our FwdLLM can converge 20 times faster than those BP-based training baselines. And this shows that our benefits not only comes from the accelerated processors, but also comes from the optimized training system itself. And second part of the evaluation is about the different client numbers. And as you can see in the figure, red lines are our BP-free training system performance. And generally, it will take like 50 clients to surpass those BP-based methods because maybe we need 100 or even 1,000 perturbations to validate those perturbations. And after that, our BP-free systems can continuously earn more benefits from the increasing of the clients. But for the BP-based baselines, they will just stop and earn no benefits anymore. And the third part is about the resource cost of our system. And the most significant improvement of our system is memory reduction. And we can reduce more than 90% of the memory compared to those baselines because we do not need to store any more activation to compute those gradients. And please remember, we do not include any quantization techniques in this work, but those quantization techniques are totally orthogonal to our systems. So I think this is a very promising research direction to make FedLLM fine-tuning can happen on more clients. Those clients have very limited memory and like TE execution environments and like the MCU or something like that. And only one negative result is about the energy cost. And though the convergence time can be amortized by the concurrent client running, they will produce a real energy that cannot be dismissed. But we expect this issue can be solved with the development of the NPU processors. And the final part of our evaluation is our system on the billion-sized LLaMA. I think more of you will be interested in this most very popular model. And it demonstrates that our system is promising to be developed into almost all FwdLLM training scenarios, including the generative and the discriminative task, where the BP-based methods can do. And as you can see in the figure in the demo, the forward-only fine-tuning model can generate a similar sentence as a model trained by those BP-based federated fine-tuning. And with the NPU simulation, we show the promising vision that FwdLLM that was training in a federated learning way with weaker training devices and longer transmission distance compared to the central training can still converge with the same speed with those central training. And that means maybe in the future, federated learning might be also widely developed or deployed, just like what our cloud computing is doing now. So finally, here is a quick summation of our work. And we first introduced the FedLLM and its challenges, and then we proposed FwdLLM that is built atop on the forward-only fine-tuning. And we have a series of optimizations to make it more efficient, including the parameter efficient BP-free training and client workloads adaptation and the discriminative perturbation samplers. And with all those designs combined, we achieve the memory-efficient, NPU-friendly, and high client scalability FedLLM fine-tuning without any backpropagation computation. And we demonstrate its efficiency on the LLaMA and believe it can be applied to more models and can be a trigger to more federated mobile applications or even general mobile training in the future. And that's all technical parts of our work. And the final slide is about our code. And we have earned 3 badges to confirm that you can reproduce our work certainly. And we also have self-developed open-sourced mobile inference engines that is called MLM. That's the second QR code. And you can deploy our system into the real mobile devices. And recently, we have released the support of the NPU inference for those LLMs in our engine. So please scan those QR codes to try our code. So thanks for listening. I'll be happy to answer any questions.